Hello student, in this video we are going to discuss Gauss law. But before discussing Gauss law we need to know what is flux and how we can calculate flux through an area. Flux, it is the number of lines passing normally through a given area is called flux. That is electric field lines. We are discussing here the electrostatics, and so the lines will be the electric field lines, and flux is the total number of electric field lines passing through normally a given area. So for that I have taken a small area, and at this point, due to this charge, the electric field E, and the direction of this electric field be along the line joining the point and the charge. Here the area is not normal to the electric field lines. It has to be made normal to the electric field lines. So ds area is in this direction, that is normal to the area given. This area ds has a direction this one. So electric field lines on this area is not normal to normal. Now first of all we have to make this ds area normal to this electric field line. So I have just turned this vector ds, area is a vector quantity. I have just turned this ds along the E, so it will be like this. And the magnitude, and we know that when we turn a vector through some angle, its value changes, and the change value or the magnitude of this ds area along this or normal to this electric field lines will be ds cos theta. Number one. Number two, what is E? In earlier videos we have discussed that electric field intensity at a point is the number of electric field lines passing through a unit area. That is, it is the density of the lines at that point. So I know what is the amount of electric field lines at this point per unit area, that is E. So total number of electric field lines passing through this ds area will be multiplied by this and this one. Once again, remember, electric field intensity at a point is the number of electric field lines passing normally through a given through a unit area at that point or around that point. The total area I have taken here, it was ds, but when it turned a normal to the electric field lines, it becomes ds cos theta. So the number of lines per unit area and the total area multiplied. So through this area, the electric flux is d phi. E, that is number of lines per unit area normally, and the total normal area. So since electric field intensity and ds are the vector quantities, we can denote them as dot product E dot ds. Now if the area is large, vast, we can calculate by integrating that small amount of electric flux through this small area. So the flux through an extended area phi can be obtained by integrating that small flux dx. But if the area is a closed surface, you mean suppose that the charge is inside a potato, then the surface of the potato or surface of a room or surface of a body, the total body is a closed surface, and in that case we denote that integration like this. This is the integration, and when we put this sign here, it becomes integration that we carried out through the total closed area. Suppose that we have to carry out or we have to calculate the flux through a cube. We have to take all that area of the cube, that is 6 faces that cube have, and therefore there will be 6 areas. So only with this method we can calculate the Friends, now we are going to discuss Gauss law. What is Gauss law and why do we need this Gauss law? Because in Coulomb's law we can calculate, we can find the electrostatic force between 2 point charges, and we cannot find the electrostatic force between charges of any kind of distribution or extended charges. But Gauss law allow us to calculate the electric field intensity due to different kind of charge distribution. So what is Gauss law? total electric flux through a given closed surface. Flux through a given closed surface. The surface must be closed, or it is not closed, it must be made closed, and surface is equal to 1 by epsilon naught times the charge enclosed within the surface. It means if some charge is enclosed within the body, there would be some flux or line coming out or going into the surface. Mathematically, this statement can be summarized into this equation, and this phi, it denotes the flux, and mathematically flux through a closed surface is determined by integration carried of this one. That is, this sign represents the integration is being carried through the whole surface of the body, and as per that statement it must be 1 by epsilon naught time Q enclosed. And here I have taken a closed body. It is a closed body, it is packed from all sides, and Q charge is placed inside it. If the total number of electric field lines coming out of this, if the charge is positive, the lines must be coming out of this body, and that must be follow the rule. It should be normal. To each and every point of the surface. And if the charge is -1, the lines must be going into the body, and that must follow the properties of electric field lines. Now we will derive, or we will prove the Gauss law. We are going to derive or prove the Gauss law. For that I have taken a closed body, and within it I have taken a charge Q enclosed, and I am not writing enclosed completely because it will create some problem here. So I have taken only QEN. EN means enclosed. At this point I have taken a small area ds. So this area is in this direction, normal to the surface, so this direction, and the electric field because of this charge at this point is along this line E. Now to calculate the flux, we need to rotate this vector normal to the electric field line. So ds cos theta is the value. Now what is the electric field intensity at this point? Since this point is at a distance of r from the charge, so electric field intensity at this point is 1 by 4 pi epsilon naught Q enclosed by r square. Since we can calculate phi using this formula for a closed surface, surface integral of the closed surface, and to remove this dot I have taken ds cos theta, and E, the value of this value has been taken here, and now the equation become like this. What are the constant quantities here? That is Q enclosed, that, and 1 by 4 pi epsilon naught is out of integration sign, and ds cos theta by r square. This ds cos theta by r square represents a small solid angle because due to a surface at a point at a distance of r. So this is the surface ds at a distance r from here. So the solid angle made by this small surface at this point will be ds cos theta by r square. But if this integration for this one is carried, d omega, it will be 4 pi, because to understand this, look at me. If I can see the room, the half of the room is making a 360 degree angle at my eyes, but when I turn around, again the half of the room is making 360 angle at my eye. So the total angle, a closed body within its any point within the body makes an angle of 4 pi totally. So that total solid angle will be 4 pi. So 4 pi cancelled out, and finally we get the flux is 1 by epsilon naught Q 1 by epsilon naught times the Q enclosed. That's all.
Okay.
Students, here is another simple method to derive Gauss law or prove Gauss law. Here this is a spherical body, sphere. I have taken its radius is r, and a charge Q has been enclosed within this. This surface is called Gaussian surface. a small area ds of this surface has been taken ds. So the direction, since it is a sphere, its direction will be normal or radial to the sphere, and the electric field intensity at this point because of this charge is again radial along will be along the radius. Its value can be calculated using Coulomb's law, 1 by 4 pi epsilon naught q enclosed by r square. From the formula calculating flux, phi equal to surface integral carried over through the total surface. So this is E dot ds. Since ds and E are parallel to each other, so angle between them is 0, and as per dot product, E ds cos theta, and theta is 0 here. In place of E, I have taken 1 by 4 pi epsilon naught q enclosed by r square and ds. These things doesn't depends on the integration, or it will be same at every point of the surface because the distance is same, charge is same, and these are the constant quantity. So taken out from integration, so total surface area should be calculated or integrated, and the total surface area of this sphere we know that will be 4 pi r square, and 4 pi r square cancel out. Finally we get 1 by epsilon naught into q by enclosed. Here are few special cases we should discuss. Number 1, if q enclosed is 0, that is if the body contains no charge, then as per formula you can see there will be no lines coming out or going into the body, that is total flux through that body will be 0. Next one, if q enclosed is greater than 0, and you know that if the charge enclosed is positive, the lines must be coming out of the positive charge. So the lines coming out of the surface like this, the charge enclosed here is positive, so lines must be going out. Next one, if the q enclosed is less than 0, that is if it is negative charge enclosed within the body, then from property of electric field lines we know that the lines must be terminating at that negative charge, so lines must be going into the body here. So it is called negative flux, this is called positive flux. When the charge enclosed is positive, lines must be going out, and it is called positive flux, and if the charge enclosed is negative, the lines must be going inward, and that inward flux is called negative flux. Next, if there are large number of charges enclosed within the body, then according to additivity of charges, we must calculate the total charge of the body. Remember, the position of the charge don't have any effect on the flux. So the total charge of the body will be calculated using additivity of charges. Now flux will be 1 by epsilon naught, and the total charge enclosed within the body. Third one, the last one, if charge is outside of the body, then you can see the lines is going into the body, but it is coming out of the body also. So number of lines entered 4, and the number of lines come out, that is again 4. So these are the negative flux, and these are the positive flux. So the number of flux or amount of flux inward outward cancel out each other. Note that flux is independent of the size of the body. So how can we understand this? Suppose that there is a small body and a charge q is enclosed within it, the flux will be q by epsilon naught. But if the body is large and very large, and the same charge is kept inside this body, again the number of lines and the flux will be the same. Students, here is a very important application of Gauss law, and using Gauss law we can deduce the Coulomb's law also. Here I have taken two charges, point charges q1 and q2, and we need to find the force between these two charges. The distance between them is r, and to apply Gauss law, first of all we need a closed surface. So here I have taken a sphere of radius r and centered at the charge q1, so that q2 remains on its surface. Its work will start later. First of all we will discuss Gauss law, or we will implement Gauss law on this surface. So according to Gauss law, the total electric flux coming out of this surface will be q1 by epsilon naught. And E dot ds, the surface here I have taken a small surface ds that will be along the radius of the sphere, and the electric field intensity E at this point will be again along the radius. So E ds cos 0 degree taken q1 by epsilon naught. Cos 0 value is 1. E ds has to be integrated and q1 by epsilon naught. And ds, what is the total surface area? Total ds of this sphere, that is 4 pi r square. When we put this in the denominator, we get E equal to q1 by 4 pi epsilon naught r square. It is similar to the electric field intensity determined by a point charge at a point. Now what will be the force on this charge q2? And according to the definition, force will be q into E. So q into E, that is that what is the charge q here, that is q2, and what is the electric field intensity here, that is E. So I have taken, and finally when we put this value here, we get 1 by 4 pi epsilon naught q1 q2 divided by r square. The direction of the force will be same as that of the direction of the electric field. So to show this direction, I have taken a unit vector r, so that represent the direction of the electric field as well as the direction of the force.